we left off in first semester talking about antiderivative, right? And the idea there was that if we started with some function, could we recover the function that if we differentiated that, we'd get that derivative, right? So we're trying to formulate a process to go backward. Some of the big takeaways that this antiderivative is never unique, right? Because you can always just tack on some constant to the end, and that constant dissolves during differentiation. But there's infinitely many kind of antiderivatives, right? So that was the idea from 410. In 5.1, we look at this idea of like accumulation. So if you have some rate, something happening at a rate, and you have some duration, and you multiply those things together, you get some like measure of accumulation, right? If you're driving your car at 50 miles an hour and you drive for 2 hours, you've gone 100 miles in that time, right? So this is like a real intuitive idea if we think about this graphically. So like this is our miles per hour, and this is like hours down here. So if I'm looking what distance we accumulated in, say, time t, I'm looking for like the area under the curve, right? Is everybody okay with this idea? Okay. That's the big idea from section 5.1. It's just that if I do a rate times a duration, that's going to lead me to some measure of accumulation, which is going to be the same as the area under a curve. Hey, fellas. Does that feel okay? That's about what you should have taken away. It would have been mostly like just kind of doing that. So in section 5.2 then, let me just make sure I'm looking at this. What we say is, okay, that's all well and good if I have, like a table of data, like if I have some x's and some y's, I'm going to call these actually dy dx's because they're rates. So even if this isn't like a smooth curve, but I just know some values, I can approximate this area. So if I think about it, 2, 3, 4, 5, 6, 7, 1, 2, 1, 2, 3, 4. So if I were to say plot this, I have some, I don't know what the function is doing in between, but I could like approximate it by doing something like this, right? So what I can do is I can build what's called like a Riemann sum. So if I'm using like a left-hand Riemann sum, I'm going to take the left x value, and I'm basically going to make a rectangle. And I'll add up those areas. So it would be like 3 plus -2 plus 5. If I did this with like a right Riemann sum, so I'm going to use the right hands then as my heights. So that would be -2 plus 5 plus 7. Or you could do like a midpoint. Where you take like the average of the two. Oops, that first one is too high. It's supposed to just be like that. So it'd be like 1/2 plus 2.5 plus 6.5. Oops, just 6. Everybody's okay there? And like the fourth way you could do this is you'd make like a trapezoid. So there you're going to have like, remember the area for a trapezoid is 1/2 B1 plus B2 plus or times H. So like, those are like your Y's, and the H is like your change in X. So it'd be like 3 plus -2, well, 1/2, 3 plus -2 times 1, and then 1/2, -2 plus 5 times 1, plus 1/2, 5 plus 7 times 1. And it turns out that that's going to be the same as our midpoint rule here. In this case, yeah.
If the left is like the -2, then why is the midpoint 2.5?
Because I averaged, it should be 1.5 then, eh? Thanks. But you're just averaging those.
Yeah.
Okay. So any of these gives you an approximation, right? Some of them might be overestimates, some might be underestimates, depending on if where the function is increasing and decreasing at. But like, that's the gist of it. Does that feel okay? So what we did in 5.2 then is we said, okay, what if instead of having like, you know, like a curve that's piecewise linear, or even just a curve that's approximated by, you know, or where I know just specific data points. What if I have like some smooth curve and I want to find the exact area underneath it? Well, what we did in section 5.2 was we essentially did the exact same thing. We're going to build, you know, like just a bunch of Riemann sums. Oops, it's a little fat for my liking. You know, like doing one of these guys. Everybody's okay with that? Where this is like some width, right? So what we said, or what we observed here, is as the width of those rectangles gets smaller and smaller and smaller, our approximation gets more and more and more accurate, right? So the idea here is that we just want to take, you know, like our area under curve is going to be the limit as that width approaches 0 of f of xi, I should need a sum I equals 1 to n of f of xi times delta x. Is everybody okay with that idea? That's the takeaway from section 5.2. Is that okay? If I want to find the exact area under the curve, I no longer want an approximation, which is not possible to get geometrically unless I have something that's piecewise linear, composed of geometric figures like parts of circles and then like, you know, parts of rectangles or parts of triangles or something where I can like piece it together geometrically. If I just have some like smooth curve that isn't resembling any geometric figure, I'm going to do the same thing. I'm just going to fill it up with Riemann sums, but they're going to be infinitely narrow so that we can make a precise approximation. And it turns out here, like I just called this f of xi when I drew pictures with left-hand Riemann sums. Turns out it doesn't even matter what point you use, whether it's a left or a right, or even like any arbitrary point inside that interval. If I use that as the height of my rectangle, it doesn't matter. I'll get the same exact answer because once my rectangles become infinitely narrow, they're all the same point, right? Because when they become width of 0, it's just like just one value. So I think the textbook uses like a star here to indicate that like just some x value on, you know, each interval. Okay. So what we have then, if I do like a little example here, so let's say I want the area under the curve from 0 to 3 for the function f of x equals x cubed minus 6x. So my area is going to be the limit as n approaches infinity. Well, we'll introduce that notation in a minute. delta x approaches infinity of the sum from I equals 1 to n of f of xi delta x. So from 0 to 3, that tells me my delta x is going to be like 3 minus 0 over n. So I'll just call this like a and b arbitrarily for a minute. So I could instead write this then as n goes to infinity, that width is going to go to 0 then, right? And I want to do this, rewrite it this way, because I want to get everything kind of in terms of one variable, right? Instead of having n's and delta x's in here, now I've gotten just n's everywhere. So like n is changing, so I'm getting n subdivisions, and I'm splitting them into width, infinitely small width. Is that okay so far? All right, so with the tools that we have to do this, then we have, let's fill some stuff in. So my f of x is xi cubed minus 6 times xi, and my delta x is going to be 3 minus 0 over n. So far, so good. I want to now come up with an expression for these xi's that are in terms of n. So if I think about this, we have like 0 to 3, right? If n equals 1, x should add up to be well, this distance needs to be 3 in total, right? So I know the sum of my xi's has to equal 3. Everybody's okay with that? So if I take each of these distance to be 1 over n of them, and I add up n of them, how many do I get? What is the total? If I take n 1 over n's and add them together, if I add 2 1 over n's, I get 2 over n. If I add 3 of them, I get 3 over n. If I add 4 of them, I get 4 over n. If I add n of them, I get n over n, right? So if I need that to add up to be 3, I just need those to be like 3 over n's then, right? 3 over n plus 3 over n plus 3 over n plus 3 over, add that up n times, I'm going to end up with 3n over n, which is just 3. That's my whole total. Is that okay on how I got to that? So we have 3 over n cubed minus 6 times 3 over n times 3 over n. Oops. We need like I there though. Let me explain where the I comes from.
Can you explain the real?
Yeah, so if I know that if I add up n 1 over n's, that's 1. If I add up n 3 over n's, that's going to be 3n over n, which is 3, right? And that's what all my subdivisions have to add up to, because we're going from 0 to 3. Or no? And so then I can just like tuck it inside and it should be good, right? Alex?
So if we're going from like 2 to 5, would it still be 3?
Yes. Yes. So the next subdivision here should be at like 2 over n. And then, well, I should say, this is like 3 over n. This would be like 2 times 3 over n. And then 3 times 3 over n. And then I have like 4 times 3 over n. Right? Each subinterval is going up by a 3 over n. That's why I've put the I there. Because we're plugging in a new x each time, right? You guys see that? All right. And now comes the yucky part. Which is having to evaluate this limit and sum. So the first thing I observe here is that this doesn't have an I anywhere in it. You guys see that? So that piece can come out front of the sum. Is everybody okay with the simplifying I've done so far? If I look inside that sum, I notice that I have a greatest common factor of 9 there. Everybody see that? And I have an n down here. Is that okay? I think now I'm going to distribute my summation. So I'm going to be a little bit careful here about what's going on. Oops, that's n cubed, or I cubed, sorry. Still okay? So if I look in here and in here, I'm going to factor out of the sum all the parts that aren't dependent on I. So from that piece in green, I can take out a 3n squared. And from the part in yellow, I can take out a 2. This and this now, we have established formulas. So these were things you could Google, or they're in your textbook in the section 5.2 that would have been presented to you. So the sum of I cubed is this, and the sum of I is this. Oops. So now we've gotten rid of all the summations, right? Now we can start working on the limit piece. So I'm going to look at the limit here first. Let's do this. What kind of function are we trying to take the limit of? That 81 over n to the 4th times n plus, or n times n plus 1 over 2 quantity squared. What type of function is that whole thing that I've highlighted in green? Should recognize that as a rational function, right? It's just a polynomial over a polynomial. Everybody's okay with that? And since the limit that we're looking at is going to infinity, all I really care about is the leading coefficient of the numerator. Well, I care about the degree of the numerator and the degree of the denominator, right? If I look at the degree of the numerator, what's the degree of n times n plus 1? That's degree 2, right? I have an n squared in it. And if I square that, then the degree is 4. What's the degree of the denominator? 4. So the limit here for this piece is just going to turn into the leading coefficient of the numerator over the leading coefficient of the denominator. Is everybody okay with that? Same idea over here, correct? Another rational function, polynomial over polynomial. The limit's going to infinity. I care about the degree first. The degree of the numerator is 2, and the degree of the denominator is 2. So it's just going to be leading coefficient over leading coefficient. Everybody's okay with that? If I make a common denominator, then I end up with that. Here's the good news. We're never going to do it this way ever again. Okay? This process that we've just looked at, so this is akin to doing a limit this way. Did I ever ask you really to do this? It was just like a stepping stone, right? Do we need to know the definition, know the notation? Yeah, but only in so as much as to like be able to do a limit easier, right? So this whole area under the curve then, we give a new name to, or a symbol to. We write it this way. So this symbol is the integral symbol. It should look like a stretched out S. S for sum, because that's really what we're doing when we're taking the integral of something, is we're doing a summation. We just, once we get into section 5.3, we will never use the summation to do this again, algebraically anyways. If we're doing it geometrically, yes, we might add up pieces of a, areas under graph, particularly if we're not given the function. But that's the idea. That's what the gist of 5.2 was. Okay. Let's pause here. That's an overview of what we should have taken away from those 3 sections. We're going to connect those 3 sections together in section 5.3, but if we're not ready to start that yet, I don't want to rush into doing that if we're still kind of sorting our way through 5.1 and 5.2 since I've been gone. What I'd like to do next is to just take some questions that you guys might have from homework. So you guys should have ideally started and finished the 5.1 homework. That should have been relatively okay, where all you're doing is basically like multiplying things up and adding them together. But anything from 5.1 or 5.2 that you'd like to talk about before we get going, I'd like to take some time and do that now. Ryan? 5.1, number 24. Sure. Of course, yes. Yes. All right, let me find the get that out. Two, 24. Did that little overview, before we start in on these questions, I'll get to those real quick. Did that overview kind of help connect these ideas together a little bit better than maybe? Okay. Section 5.3 is the big payoff where we take 4.10, 5.1, and 5.2 and combine it all together and show you that it's really all doing the same thing, which is the big payoff there. All right. It says on 24a, use definition 2 to find an expression for the area under the curve y equals x cubed from 0 to 1 as a limit. So if I go back and I look at definition 2, let's just drop that in here also so we can look at it at the same time so you can see what I'm doing. Okay, So my f of x here is x cubed. Everybody feel good there? Tells me in the problem. My delta x is going to be 1 minus 0 over n, or just 1 over n. Does everybody feel okay there? And then my xi is going to be well, my first subdivision is from 0 to 1 over n, right? My second subdivision is from 1 over n to 2 over n. And then from 2 over n to 3 over n. So as I'm changing those, the numerator of that is changing from 1 to 2 to 3 to 4 to 5, all the way up to n over n, which would be my last subdivision from n minus 1 over n to n over n, right? So my xi should just be I over n. So if I put this together, I'd say this should be the limit as n goes to infinity, the sum I equals 1 to n of I over n cubed times I over n. Or you could write out the summation in an expanded form like this if you'd like. That's fine to do it that way as well. So if you're doing that, this is just like 1 over n for x1. This would be like 2 over n for x2. This would be like n over n for xn. Yes?
Why do you have the times I over n like that?
That's the delta x.
Oh.
Right? That's my delta x. So that's tacked on to every term, so I can just write it that way. Does that feel okay, Ryan? Okay. And then in part B, it says the following formula for the sum of cubes, or the sum of the cubes of the first n integers is proved in Appendix E. Great. Use it to evaluate the limit from part A. Oops, I did not mean I over n. I meant 1 over n, because that's my delta x. Excuse me. Okay, so we're basically just going to do the same thing that we did before, right? So I'm going to take that 1 over n, and I can pull it out front of the summation because it doesn't depend on I. And just like we did, we can take that n cubed and pull it out front of the summation because, again, that didn't depend on I. And now I can use that formula that it gave me and I'm, again, doing a limit of a rational function. It's an infinite limit. So first thing I care about is the degrees of my polynomials. The degree of the denominator is 4. And the degree of the numerator is 2 squared. So 4. So my limit should be leading coefficient of the numerator over leading coefficient of the denominator, and I'm done. Does that feel okay, Ryan? So it's the same process that we did in the example that I showed you, that like we're not really going to have to do integrals this way, but this is understanding the definition. I think it helps to do it the hard way and see kind of like what exactly is this a shortcut for. when you're in elementary school, you don't start with the times table. You don't learn 5 times 4 is 20. You add 5 up 4 times and show that it's equal to 20 before you start using the shortcut. It's the same idea here. We're just showing you the addition problem that you have to do, that you're shortcutting through by doing this other thing, which we haven't shown you how to do yet. So if you're like, what other thing are you talking about? It's like, we haven't seen it yet. It's the antiderivative. Is coming back here in a big way. Okay. Ryan, you're happy though? Okay. Other questions from either 5.1 or 5.2? Addie. 5.1 number 22? Sure. Okay. So it says, use definition 2 to find an expression for the area under the graph of f as a limit. Do not evaluate the limit. So all it wants is that. Oh, 22. Excuse me. I thought you said 21. My apologies. No, it's no problem. I'm sorry. Okay, so it says determine an area under the curve, or I'm sorry, determine a region whose area is equal to the given limit. Do not evaluate the limit. Everybody's okay with that? All right. So there's 3 things that I'm going to need to know. I'm going to need to know what f of x is. I'm going to need to know what a and b are. Well, no, that's really just it. I need to know f of x, I need to know a, and I need to know b. Everybody's okay with that? Okay. I'm going to start with this piece. What is that piece representing? That should be my delta x. Because notice that there's no I as part of that. So I know delta x is b minus a over n. And that's going to be 2 over n. So what that can tell me then is that b minus a is equal to 2. Or in all reality, b is a plus 2. So far, so good. So if I figure out what a is, then I know exactly how to find b. So far, so good. Okay. The next piece I'm going to do is figure out my f of x. So that's going to be looking at all the parts that have an I involved with them. So this stuff is going to be like my xi. In there. So this is just going to be like xi to the 10th or something. Everybody okay there? And my xi then is going to be this 5 plus 2i over n, right? So as I goes to n, or goes from 1 to n, I'd have 5 plus 2i over n, and then 5 plus 2 times 2 over n, and then 5 plus 3 times over n, all the way down to this, right? Does that make sense to you guys? So if I think about this on the number line, my first subdivision starts here at A and ends at 5 plus 2 over n. My second subdivision starts at 5 plus 2 over n and ends at 5 plus 4 over n. What is A looking like it's going to be? 5. Yeah, exactly right. So this looks like my A. Addie, does that feel okay? And again, I'm doing way more than I kind of need to. Once you understand what you're looking at, you can look at this and fill it in. I'm just trying to give you like the over explanation of how I'm coming up with, or how I know what the things are. So that's 5. So that's 7 then, right? So I can say this then is the integral from 5 to 7 of x to the 10th dx. It's not the only way to represent that, but that's, I think, the most obvious answer. Does that feel okay? And this kind of problem, I would say, is the key problem from 5.2. As far as a multiple choice problem, being able to go back and forth from a integral to the limit of the sum, being able to go back and forth between those two notations is the big takeaway. That's the skill that I would expect to see come up in a multiple choice question on an AP exam. Is that okay? Anyone else on homeworks? Happy to do more. Okay. Question for you guys then before we move on. What do you need from me right now to feel better about what we've been doing? Obviously, this is a nice first step, but I'm not so naive to think that this like fills in all the blanks for everybody. Would you like to see the start of 5.3 to see how all these ideas are going to connect together? I think that'll, giving some context, might make, as you're going through and doing these things, seeing how this is all going to fit together, helpful. And we can always slow down after that and kind of reinforce the connections. But really 4.10, 5.1, 5.2, and 5.3 are like all telling the same story, all trying to get to where we are in 5.3. So I think it's helpful to kind of get the ending in there and make the details a little bit more, oh, I see why that was an important detail now, or I see why we did it that way. That would be what I would like to do if you guys are on board with that. Don't feel like hopelessly lost over your heads. That would be what I'd like to do. Now, if you feel that way, we can stop and do something else and reinforce some of these ideas we've seen to this place. But if you're like, think I kind of get the gist of it, the details maybe, don't feel great about, but like the big idea we're talking about here, I feel okay with what we've been trying to do. My ability to do it myself, I don't feel great about, but like I understand at least conceptually what we're trying to get to. Okay, if no one's objecting here strenuously, well, let's go ahead and start this idea. So, bless you. for section 5.3, we're going to start by defining a very special function. This function links the ideas, or, oops, come on. Okay. Links what we were doing in derivative calculus to these ideas that we've been developing now in integral calculus. This function is like an accumulation function. You can think about it as like the area so far. So we define a function g of x that's equal to the integral from a to x of f of t dt. So let's say that this is our function. Here are the blue curve is the graph of y equals f of t. Here's x. And so my value for g of x is going to be the area under f of t up to that value x. So when x is 1, it's something. When x is 2, it's, it'd be a little more in this case. When x is 3. Does everybody feel okay? I should really say a plus 1 and a plus 2 and a plus 3 because it's starting at a. We don't know what a is. So far, so good? Okay. All right, so let's look at an actual numeric example to help us kind of work our way through this. So we're given a graph of f of t. And we're asked to find the values of g of 0, g of 1, g of 2, g of 3, g of 4, and g of 5. And then we'll sketch a graph of what g would look like. So g of 0, well, that's the integral from 0 to 0 of f of t dt. Well, if my rectangle has 0 width, how much area can it have? Has to be 0, right? Everybody's intuitive sense tells you that right away, right? A line is a one-dimensional figure. There can be no area. Okay. So g of 1 is going to be the area of, it's going to be that, right? So to do the area of a triangle, that's 1/2 base times height. The base is 1, the height is 2. So 1/2 base times height is just 1. So g of 1 is 1. Still feel good? Okay. So if I do f of 2, it's this. But I'm really going to think about it as just my answer for g of 1 plus this next rectangle. Is everybody okay with that? So this is my answer for g of 1, right? And then I have this next rectangle which has width 1 and height 2. So if I add that stuff all together, I get 3. So g of 2 is 3. Does that feel okay? All right. So g of 3 now is that this section here is curved. So we can't do it exactly. What we're going to do is just make an approximation here because we don't know the function for f of t, so we can't do like a limit of a sum even. We're just, the best we can do is an approximation. So again, I'm going to break it up into g of 2. That was 3 from before. And then what is this shape most similar to? Looks like a triangle to me. That's what I'm going to approximate it as. Or I could think about just like adding up the shaded pieces. So maybe that's 0.8 and that section's like 0.5. You could eyeball it that way too. That's acceptable. That's what I did here to get the 1.3. So I approximated this is like 80% and this is like 50% or maybe 90 and 40. I don't remember what I thought there, but that's reasonable approximation. That's as good as you're going to do. So far, so good. So this one is going to be 4.3. Now we have g of 4. So I have this area and then this area. What do you notice about the second area there that we've highlighted? It's below the x-axis, so that's going to be a negative area. Remember, if we're multiplying change in x times the y, the height there is negative. We can have negative areas when we do this. That is okay. I know it feels intuitively weird to give area a negative sign, but if you think about what this area is actually representing, where it's, f of xi star times delta x, well, those f of x's can certainly be negative numbers. Okay. So we have that. Again, I am going to approximate this area because it's curved. But to me, it looks exact same as that area there. So I'm just going to use the same approximation. Just going to make it negative. So f of 4, I get to be 3. I called it 3.0 because now there's like rounding involved. It was an approximation before, so I'm trying to give like some kind of significant figure measurement there on it. I don't know. Trying to be a good communicator. And the last one is going to be f of 5. So that's what we did already to f of 4. And then plus this new piece, which looks the same as the other piece that I just added, right? So I'll do the same approximation there. So I get 1.7 then. So if I plot my graph for G then, it would look something like this. Right? I had 1, 1, and then I had 0, 0, 1, 1, then 2, 3. And then my 3 was like 4.3 or something. And then 4 was back to 3. And then 5 was like 1.7. So I just kind of plotted those points and connected them with a smooth curve. Does that feel okay? Okay. So if we ask then, is there a relationship between the derivative of g and that function f? Well, let's look at an example here. Let's go back to this picture here, right? This is the same picture we're going to look at. Everybody's okay? So I'm looking at that same picture. In order to compute g prime, the derivative of g, from the definition of a derivative, we observe that when h is greater than 0, g of x plus h minus g of x is obtained by subtracting areas, right? So the area under the graph of f from x to x plus h, remember that was what g is, it's the area under the graph, right? So going to be g of x plus h minus g of x is going to be the area under f from 0 to x plus h minus the area under f from 0 to x. What is the leftover going to be? The area under f from x to x plus h. Does that make sense to you guys? I know there's a lot of verbiage, but it's basically we're taking that area and subtracting from it that area which leaves us that. Is that okay? Okay. For small h, you can see that the figure, or see from the figure that this area is approximately equal to the area of the rectangle with height f of x and width h. Right? There's my width, and here's my height. Right? You guys see that? Mm-hmm. So that's how we land here, that g of x plus h minus g of x is approximately h times f of x. If I divide both sides by h, I get this. Do you recognize the left-hand side of that? Looks like slope, doesn't it? And then if I slap the limit on in front of that, that becomes g prime, and this approximate becomes equals. So what we've shown here is that the derivative of g of x is just equal to f of x. In other words, what we've shown is that the derivative operation cancels out the integral operation. That those two operations are inverses of one another and can cancel each other out. The same would be true if I take the integral of the derivative. Those symbols would cancel out, just like the derivative is canceling out the integral. That is a major, major result. We call that the fundamental theorem of calculus part 1. Is that if f is continuous on the interval from a to b, and then g is defined by the function g of x equals the integral from a to x of f of t dt, is also continuous from a to b, and it's differentiable on the interval from a to b, where the derivative of g is just equal to f. Or in other words, using the notation that we most commonly use, if I take the derivative of the integral, whatever the variable is here, goes into the function and we're done. Provided what? That f is continuous. Right? If f is not continuous, that relationship does not necessarily need to hold. All right, let's look at an example here. So it says, find the derivative of the function g of x. So that's going to be the derivative of the integral from 0 to x of the square root of 1 plus t squared dt. Right? What is the derivative going to do to the integral here? Cancel it out. So what are we going to be left with? The 1 plus, it's not t squared anymore though. It's going to be x squared, and we're done. Yes.
What is the DT?
So the dt is like the width. That's like the delta x piece. So that's not actually part of the function f, right? That's just like the width of the Riemann sum. Is that okay? So it needs to be there, but it doesn't really contribute anything. It's just like the integral operation is like, you know, like that's part of the operation. Does that feel okay? That's the way I think about it. All right. What about this one? If I want the derivative of the integral from 1 to 4, x to the fourth, secant t dt. What do you notice that's different about this one than the previous one? Yeah, the x to the fourth. Notice that it starts at 1 and not 0. Does that matter? What do you think? Not when we're taking the derivative. Does the x to the fourth matter? Oh, yes. Okay. So the derivative is going to cancel out the integral, right? But what we have here is like a function inside, right? So this is like a composition. This is like g of x to the fourth that we're taking the derivative of. When I did that, what did we have to use? What rule did we have to use? Chain rule, right? When I have a function inside of another function. You guys see how that this integral where I have a function x to the fourth in there is like a chain rule? So I'm going to have the derivative of the outside times the derivative of the inside. Everybody's okay there? We catch that? You know, so it's just like a standard chain rule problem, right? Just have to make sure you're thinking about that the right way, but the chain rule is working exactly the same way. Yes.
Explain how you got like the first part red next to the right, the first part purple.
So the purple part is just me rewriting the problem using like g of x equals this. So if I'm doing the derivative then of g of x, I should say g of x equals this, right? So this thing then is, I should say, this thing is g of x to the fourth, right? And then if I do the derivative of that, that screams chain rule to me, right? So I was just trying to rewrite it in a way that made it obvious, where you could see why I needed to apply the chain rule.
Wait, so is anything like low part cancels out?
So the integral still cancels out with the derivative, right? All that stuff is gone now. And I've replaced the t with the x to the fourth, just like we had before. But I also have the chain rule piece where I have the times the derivative of the inside. Is that, you see what I'm trying to do now? Okay. Yes, Nate?
So if I see that the integral inside of the line, I could just cancel it out by doing t over to get the x.
If you take the derivative of an integral, they cancel each other out. Yes. So those things cancel each other out. You wouldn't want to do that unless it's like you're trying to take the derivative of g of x, like unless you needed to do like find mins and maxes or something on g of x, then yes, by all means, take the derivative of g, cancel the integral, and continue to do like set f then equal to 0 and do your first derivative test stuff. All right. Now it's time for this is the big payoff here. This is the key idea that we've been building for since 410. This is how the antiderivative connects to this idea of areas that we've been working on. So if f is continuous on the interval from a to b, then the integral from a to b of f of x dx is equal to f of b minus f of a, where cap f is any antiderivative of f. This is the fundamental theorem of calculus part 2, basically telling you how to do or connects the idea of the antiderivative to these areas that we've been working on. So we'll start by, to do this, we'll do the antiderivative of e to the x. What is the antiderivative of e to the x? E to the x. Then that needs to be evaluated from 1 to 3. And you can type that in your calculator or whatever, and you're done. That's the area under e to the x from 1 to 3, without doing any limits, without doing any sums, without computing areas and drawing any picture. Entirely algebraic. I've now connected this idea of the antiderivative to this area, this idea of area under the curve, or limit of the sum of these Riemann's or rectangles. How beautiful, how simple is that? Like, that's what we're trying to get to. All of this buildup was to get to here, where we've connected the antiderivative to this idea of integration. That's the payoff. Much in the same way where you start learning like the power rule for derivatives. It's like, why were we doing all this limit nonsense mumbo jumbo beforehand? This was so easy. Same idea here. We had to build up the theoretical so you can understand what to expect property-wise. You can see the connections between the two different branches of calculus, the integral calculus and the differential calculus. But that's the idea. I have some more examples here, but we're basically out of time. We can do some more example next time. Okay. For your guys' homework, I don't need you to start 5.3 yet. We'll finish these examples in class. What I would like for you guys to do, though, there is a on the MyAP, there is a 5-question homework quiz thing for today. You can do that. That would be great. It's going to cover what we would have done last time in 5.2 that we kind of went through today. And then I think limits was the other topic, the review topic in there. So the homework quizzes for this semester are going to be primarily coming from the MyAP. I'm going to have stuff that resembles what we did in the previous lesson, plus one review topic from semester 1, so we never get kind of too far away from those things. But it'll just be 5 questions. If it's multiple choice, we might get into some free response stuff at some point, but for right now, it's just going to be multiple choices for a while. Okay? Have a good day, folks. Hope you feel better about what we're doing.